So in this tutorial we're going to work out some probabilities, and we're going to use the combinations method. In fact, we're going to use two combinations method. We're going to start with the one that we developed in the last video on independent probability, but we're also going to introduce a more advanced method that we're going to use to check the first method that we're going to use, so that we have two different ways of solving the same problem. The problem we're going to work on is two kings and a jack drawn. What's the likelihood or the probability that we're going to be able to draw two kings and a jack, from a standard deck of 52 cards? Okay, well, let's start by thinking about the probability tree. Now, I can't draw out the whole tree, but I can begin to think about the branches, and they're going to be three branches going out something like this, with successful outcomes on those three events. In other words, I'm going to have first a king in this example, then another king, then a jack, and drawing the king, the probability is going to be, well, there are 4 kings in the pack, so 4 out of 52 in a standard deck of cards. The next arm is going to be 3, because I've already drawn one king, so there's only 3 left, so we've got 3 chances out of not 52 anymore, but 51, because I haven't replaced the first card that I drew, and this is why it's non-independent. Now I've got my jack. Well, there are 4 jacks still left, and there are 50 cards left in the pack. So this particular branch, to get king, king and jack in that order, would be 452 over 52 times 3 over 51 times 4 over 50. Okay, but I only want 2 kings and a jack in any order. So I could have drawn a jack, a king and a king, and that would have been the same. In fact, what I should ask myself now is, how many different orders are there? So what I'm asking is, how many combinations are there, instead of what are all the permutations? So how many combinations are there of 2 kings and a jack? Well, there are 3 things here, and so I can write 3, choose, well, 2, or I could be thinking about 3, choose 1. Would there then be 2 things? Now, it would be exactly the same if I wrote down 3, choose 2 or 3, choose 1. So 3, choose 2 equals 3, choose 1, so it doesn't matter which one I calculate. 3, choose 2 is going to be, well, 3 times 2 factorial over 2 factorial times 1. So it's going to be 3 times 2 factorial over 2 factorial, which is equal to 3. So good. So now I know there are only 3 combinations that I need to find here, and those 3 combinations are pretty easy to figure out. If I draw out my branches again, so there we go. That can represent the 2 other arms that we've got. This time I'm going to think about drawing maybe a king, and then a jack, and then a king, so that's still 2 kings and a jack. Or the other option is when the jack is in the first position, so that would be jack, then king, and then king. So that exhausts the number of combinations there are of taking 2 kings and a jack. But what are the probabilities as I go along these branches? They're going to be not exactly the same. The fractions are going to be slightly different. Let's have a look. So first of all, for my king, I'm going to have 4 out of 52 again. But here, when I go to my jack, I'm going to have 4 out of 51, because I've only drawn 1. So it's different to this fraction here. So 4 out of 51. And now if I think about my last king, well, I've got 50. So it's going to be, I've only got 3 left, so it's going to be 3 out of 50. So the 3 out of 50 instead of the 3 out of 51. Let's do this one. So the jack, I've got 4 out of 52 this time. Then I've got my 2 kings, so it's going to be out of 51, then out of 50, just as with the other branches. But it's going to be 4 out of 51 here, and 3 out of 50 here. Okay, and that's all of them. Now let's have a look at them very carefully. What I can do now is multiply across. So I've got to multiply as I go across my probability tree. So I'm going to multiply the numerators and multiply the denominators. So in this case, it's going to be 4 times 3 times 4. With every branch, it's going to be 52 times 51 times 50. In this branch here, instead of 4 times 3 times 4, it's going to be 4 times 4 times 3. Well, that's the same as 4 times 3 times 4. So in fact, the outcome here, the product of these 3 fractions, is going to be exactly the same as in the first branch that I drew out. And it's going to be the same here as well. In the third branch, I've got 4 times 4 times 3. Well, that's the same as well as 4 times 3 times 4. So it really doesn't matter that these are different fractions, because at the end of the day, they are going to come to the same product. So if I rub these out and just think about the first branch, just as we did with independent probability, I know that for these 3 combinations, it's going to be the same. I'm going to be able to multiply these together, multiply by 3, and that will give me an answer to what's the probability of drawing 2 kings and a jack. So let's do that. So we've got 4 times 3 times 4 out of, and I can just do one fraction bar here, 52 times 51 times 50. Okay, now 4 out of 52 can be simplified as 1 out of, let's draw a fraction bar here again, 1 out of 13, so divide top and bottom by 4. 3 out of 51, well, there are 17 3's in 51, so I can divide top and bottom by 3 and I get 1 and 17 then. 51 divided by 3 is 17, and here I can simplify this to 2 out of 25. So now I've got a much simpler thing to deal with. In fact, if I just erase the top here, I've got 1 times 1 times 2. I can just say that's 2. Saving a bit of space here because we're going to need the space for the check that we're going to do in just a moment. Okay, so now I've got 2 out of 13 times 17. Well, that's 221 times 25. And whenever I've got a 25, I like to simplify that by multiplying that by 4. So I can divide that by 4, give me 100, and if I divide that by 4, I've got 110.5. So that's going to be 55.25. So 55.25 times 100 is going to give me 5525, in other words 5,525, and the numerator is still 2. So I've got an answer. Now what we haven't done is multiplied all of that by the number of combinations, so all of that is times 3. So if I now put, so this will be 3 times all of this, or I can just put that in the numerator here, times 3 times 3. So 2 times 3 is going to be 6. So when I multiply by the number of combinations through the tree diagram, I get the answer 6 out of 5,525, and that's the probability of drawing 2 kings. Now, for the second method, I'm going to check, again using a combinations approach. In fact, this is going to be using a full combinations idea. and you'll find it be a bit simpler, maybe a bit quicker. Also, it will give us a way of checking this result. So let's write check. We'll do it in a different color so you can see what's going on. The way to think about it using this idea is that we've got, well, 2 kings. So I'm going to think about it in terms of having 4 kings in the pack, and I'm just choosing 2. So I can write that, in fact, as 4, choose 2. Now, using something called the fundamental principle of counting, if I then think about the 4 jacks, so 4, choose just 1, I can multiply those together. So the fundamental principle of counting says we multiply together the 2 different operations here. That gives me the numerator, in other words, the number of ways, the number of combinations that I have, the number of ways I have of getting 2 kings and 1 jack, out of what? Out of the number of combinations, the number of ways there are of drawing cards out of the pack, drawing 3 cards, in fact, out of a deck of 52. So I can write that as 52, choose 3. And if I work these 3 values out, I should get the same probability as I got here. In other words, 6 out of 5,525. Let's see if we do. Okay, well, the 4 choose 2 and the 4 choose 1 are the easiest, so I'm going to start with that. Let's do that over here. So we've got 4 choose 2. Well, that's going to be, if I think about it, maybe up here, 4 times 3 times 2 times 1 in the numerator. But that's going to be 4 times 3 times 2 factorial. Okay? So I'm doing that because in the denominator I'm going to have n minus r, so that's 2 factorial, and r, which is also 2 factorial. So I'm going to have 2 factorial, which is 2 times 1 times another 2 factorial, which means these are going to cancel. This gives me 4 times 3 divided by 2, in other words, 6. It's a nice, easy choose function. And of course I could just find this on the calculator, but it's quite satisfying to do it by hand. So 4 choose 2 is 6, and 4 choose 1, well, that's going to be 4 times 3 factorial divided by 3 factorial times 1. In other words, it's just going to be 4. So times 4. So the numerator, that's the easy one. Let's do the denominator. Again, I could use a calculator, but just to show you, it's pretty simple and very satisfying to do by hand. So we've got, let's work it out down here, we've got 52 times 51 times 50 times 49, and I'm going to just write factorial here, so in other words it would keep going, divided by, well, n minus r, to give us the permutations, n minus r is going to be 52 minus 3, 49, so that will give me 49 factorial for the permutations, and then to get the combinations I multiply by r, which is 3, so 3 factorial is going to be 3 times 2 times 1 times 49 factorial, which means these cancel again very satisfyingly. We don't need to worry about this 1 here, and in fact we can do some cancelling here. We can say 3 and 51 are going to cancel, so 17 and 1, and the 2 is also going to cancel, divide by 2, so I've got now not 52 but 26. Okay, so now I've got my denominator. 52 choose 3 is 26 times 17 times 50 in the denominator. Now I can do a bit more cancellation. 26 is divisible by 2, and so is 6, so let's just divide that by 2. So we've got 6 divided by 2 is 3, and 26 divided by 2 is 13. And in fact we've got 4, we can halve that, so 4 divided by 2 is 2, and 50 divided by 2 gives us 25. Now, to save time, I can just go back over to my calculation over here and see I've got exactly the same thing. So I've got 3 times 2 or 2 times 3 in the numerator here, and I've got 13 times 17 times 25. So exactly the same calculation. So I can go back here and write equals 6 divided by 5,525, which confirms we must have the right answer here. So this time what we're going to do is look at something a bit more challenging. We've got here, let's call this 2 black cards and 3 red cards. So we want to find the probability of drawing this combination. In other words, 2 black cards and 3 red cards. And obviously we've got a lot of black cards to choose from, a lot of red cards to choose from. So I'm thinking the probability is going to be a lot higher than this. Now, how are we going to go about this? Well, obviously a tree diagram or a sample space diagram would be very difficult to draw out. But again, we can use this technique of drawing out just one branch of, let's draw it here, the tree diagram, this time with 5 arms, if you like, of its branch. So we've got 1, 2, 3, 4, 5. And what I'm going to do here, I think, is because I can choose any combination and then multiply up by the number of branches that we've got. So I'm going to go for, let's think, red card followed by a black card, followed by a red card, followed by a black card, followed by the third red. So that will do. And now we just fill in the probabilities. So again, the denominators are going to be out of 52, out of 51, here out of 50, so counting down, 49, and 48. Okay. And so, number of red cards. Well, at the moment, we've got 26 red cards, so we're going to have 26 out of 52 here. Now we've still got 26 black cards, so 26 out of 51 here. Second red card, so we've now only got 25, so 25 here. And second red card, so 25 again. And the last branch, it's going to be 24 in this case out of 48. So those are my fractions. Now all I've got to do is work out how many of these combinations we've got. So again, I'm thinking about, well, it's 5 cards, and it doesn't matter if we do 5 choose 2 or 5 choose 3, that's going to come to the same thing. So 5 choose the 2 black cards, let's say, is going to equal, well, 5 times 4 times 3 factorial in the numerator, and then it's going to be 3 factorial times 2 factorial in the denominator. So that's going to come to 5 times 4. The 3 factorial will cancel, and then the 2 factorial, well, that's just going to be 2. So number of combinations is 10. 5 choose 2 equals 10. Okay then, so what we're going to do is multiply this up and multiply by 10. So we've got 10 times, and of course you could do this in a calculator, but it's just quite fun actually to do it by hand. I've got 26 over 52. Well, because of the way I've lined this up, this is a particularly easy thing to multiply. I've got 26 over 52, which is just a half. So 1 times a half times, now the 26 I can't do much with, so we'll just have 26 over 51 times, again, a half times 25 over 49 then. And finally, a half again. And now we can do some cancellation. So we can simply take this 10 and this 2. Let's use a different colour so we can see it very clearly. This is the fun bit. 10 and the 2, so divide by 2 and we've got 1, divide by 10 by 2 and we've got 5. What else can we do? Well, we've got another 2 here, so let's divide this 26 to get 13, and I can't see much else that we can do, so I think we're done with our cancellation. Okay, let's change the pen colour back, and now we just need to multiply that out. So I'm going to say 5 times 25 is 625 times 13, and so if I use my calculator for this to save time, I get 1625 in the numerator. Okay, in the denominator then, I've got 51 times 2, well that's 102 times 49. 102 times 49 gives me 4998. So quite big numbers then in the numerator and the denominator, but if I look at them closely, I can see it's going to not cancel neatly, but it's going to be roughly equal to a third. So I'm going to put approximately equal to 1/3. But that's the exact answer, 1625 over 4998. So let's have a look at the check and see if we get the same amount. So this time using a different kind of slightly more advanced, I guess, combinations approach. This time what we've got is, well, what have we got? We've got 2 blacks, and we're choosing those 2 blacks out of 26. So we're going to have 26, choose 2, and that's combined with, so multiplying across, that's combined with 3 reds, so 26 again, 26 reds in a pack, so 26, choose 3. Out of the total number of combinations, well, that's going to be 52, choose 5. Now, if I work that out, I should get, well, let's see, in the numerator, I'll get 26, choose 2. So that's going to be 26, I'll have to keep this quite small to fit it in, 26 times 25 times 24 factorial, and then 24 factorial also in the denominator of this 26 choose 2 function. So I'm going to cancel at that point and divide by the 2 factorial, so it's 26 times 25 over 2. So that's that bit there. Now 26 choose 3, well that's going to be 26 times 25 times 24 times 23 23 factorial, and 23 factorial in the denominator as well cancels, and so I'm left with, whoops, let's do that again. I'm left with 3 factorial. Oh dear. Let's have another go at that. I've just got a bit of a wobbly line at the moment. So there we go. So 26 times 25 times 24, what was I doing? 3 factorial. 3 times 2 times 1. Hopefully that's neat enough. Okay, so now what we're going to do, we can do some cancelling. We've got 1, we've got 13. Okay, what else can we do? We've got 1 here, we've got 8, and that 2, well that will cancel with that 26. So we've got 1 here, all 1s at the bottom now, and we've got 13 here. So I can see now that what I've got is 13, let's line them up, 13 times 13 times 25 times 25, Okay, times this 8 here. So times 8. Let's see. Is that right? Yes. Times 8. Okay. So the 13 and the 13, let's see if that cancels now with the 52 choose 5. Okay. Right. Now for the 52 choose 5, obviously I've got 52, 51, 50, 49, and the 48. And then I've got my cancellation with my 47 to factorial, and now I've got 5 factorial underneath all that. Well, that's going to be 5 times 4 times 3 times 2. So I'm going to have 5, let's put that under here, 5 times 4 times 3, let's put that under there, and I'll put my 2 under there. And that gives me my 52 choose 5. Again, I'm doing this for fun really. I could easily just put these values into the calculator and that'd be the quickest way of doing it. But what I can do here is do a little bit of cancellation, which is always fun to do. So we've got 1 and 13 here, and that 13 is going to cancel, so we've got just 1 over here. So that's got rid of all of that there, which is rather satisfying. Okay, here we're going to have 17. It's difficult for me to fit in, but if I put that there, that should be nice and visible. And here we've got 10. Okay, here we've got 24. Right, now that is a bit difficult to see, so I'm going to rewrite that over here so we can see what we're left with here. There might be a bit more cancelling we can do. 13 times 25 times 25 times 8 divided by, now that all cancelled there, we have 17 here. What have we got here? We have 10, so 5 into 50 goes 10, so we've got a 10 here. And we've got 49. And finally 24. So a little bit more cancelling that we can do here. Let's see, let's get our green colour again. I can certainly divide by 5, so I've got 5 here now. 25 divided by 5 is 5, and 10 divided by 5 is 2. We've got 1 here and 3 here. And casting my eye over that, I think that's probably all we can do. Yes, it is. So that is complete. Now, what we seem to have here is something very similar to what we had before. So we've got 5 times 25. Let's get my brown pen back again. So 5 times 25, 625, times 13, exactly what I had here. 13 times 25 times 6 gives me 1625. And this time we've got 17 times 3, well that's that 51 there. 17 times 3, and the 2 times the 49, so if I multiply those together, then I've got again 4998. So that confirms this method and means that approximately 1/3 or 30, 32, 33% must be correct. Okay, finally, let's just try and understand why these two different combinations methods work, and especially the last one, which we used in the first part of this video as a check of the more standard tree diagram kind of approach. Okay, now to do this, let me just Okay, let's just think of a simpler example, because the examples we've been using a pack of cards, well, that'd be very difficult to draw out a tree diagram, and what I want to do here, which is a sample space diagram. So for the sample space diagram, we need something a lot simpler so that we can draw it out. First of all, we need a small number of events, so I'm just going to have 2 events, so just choosing 2 things, choosing twice rather. And the second thing is we can't have too many arms, so otherwise it would take a long time to draw out, say, 52 arms for just one event. So we're just going to choose from 5 things. And for that example, I'm going to go back to an earlier video where we talked about a netball team. So in a netball team, let's write the probability. So 5 people in the netball team, the probability of choosing somebody whose name begins with J only once. And this was an example we had in a previous video. Now, if I illustrate my team using colours, I've got 3 people whose name doesn't begin with J and 2 whose name does begin with J. So I've illustrated that as there we go, as red and blue. But if I think of these then as not J, or let's write O. Okay, so we've got O for other, and these, their names do begin with J, so we're going to call them J and J. So it doesn't matter what their real names are, we're going to treat them as if they're exactly the same, they're identical. And that's because we're only looking for people whose name begins with J exactly in the same way as we were only looking for 6s. We weren't trying to work out the order or differentiate between those 6s. The 6s are identical. It's the same with a pack of cards. When we're choosing from a pack of cards, if we draw a couple of kings, then we just shuffle it around in our hand. Doesn't matter what order we drew them in. Similarly, in the National Lottery, for example, when we've got we've chosen the different balls, we then just shuffle them around until we've got the order that matches the order we see on the screen. So order doesn't matter, and that's why we're using a combinations approach. Okay, so what would the sample space diagram look like in this example? Well, I've already drawn it out to save time, and you can see we've got 5 to choose from to start with, and then we've only got 4 at the end of each of these arms here. So we've got 20 possible outcomes, 20 ways of going through these, and in fact these are 20 permutations. Now, when we're using the method that we've just been using, we're not talking about permutations, we're talking about combinations. So how would we work our way through this diagram? Let's remember how it worked. What we did was we took, well, in this case we've got 3 things, and we chose just one of those 3 things. So we're saying 3 things, choose just one. And in terms of the sample space diagram then, we would be choosing 3 of these O's. So either we're going down this route, or this route, or this one. So those are the 3 options, and this is the one direction that we're going to be going down. Okay, and the next thing is we multiplied by 2 choose 1 in this example, so it'd be 2 things, we're just going to choose 1, so times 2 choose 1, and on the sample space diagram you can see exactly that at the end of this branch here. So in the second event here we're choosing either that or that, so those are the 2 things we're choosing. Sorry, gone down the wrong route, haven't I? Okay, let's just erase those. So we're not choosing those 2. No, we're choosing a J because we didn't choose a J in the first round, in the first event. So it's either that or that. Okay, well that's if we went down this route. But it's 3 combinations of that idea. So we're going to also be able to go down this route, and again it branches into 2. Or this group, it branches into 2. So you can see very clearly here on my diagram that we've got 3 2's. 3, 2 there, 3, 2 there, and 3, 2 there. So 3 times 2. Now the alternative, of course, let's do this in a different colour pen, would have been to go in the opposite direction, but then we'd get a repeat. So we're either doing this or we're doing this. We're going up here or up here. So that would be 3, choose, sorry, it's not 3, it's 2. So in this case we've got 2, choose 1, times 3, choose 1. So let's have a look at the 3. So at the end of the branches again we've got either this, this, or this. So there's our 3, and we're just going to have to obviously just choose one of those pathways. Or we're going to, at this end, choose this, or this, or this. So it's 2 times 3, whereas going in this direction it was 3 times 2. But of course multiplication is commutable, so it doesn't matter whether we put that first or that first. Either way we're going to get the same result. So we've got 3 choose 1 is obviously, so this is just the numerator at the moment, so 3 choose 1 is 3, you can say, divided by 2 factorial times 1 factorial, 3 factorial divided by 2 factorial divided by 1 factorial. So if that's the way you want to do it, you could also use something called Pascal's triangle. Pascal's triangle will also give you the answer to what 3 choose 1 is, or you can just use your calculator. If you've got a button, 3 choose 1 will give you 3 divided by 1, which is just 3. So the answer to 3 choose 1, how many ways are there choosing one thing? Obviously there are 3. So the answer is going to be 3, and here, how many ways are there choosing one thing from 2? Well, obviously 2. So 2 choose 1. Again, whatever method you use will give you the answer 2. In this case, going in the other direction, we have 2 times 3, but obviously that will give you exactly the same thing, so 6. Now, what about underneath? And what we had here in both examples was 5 choose, so whatever direction we're going in, it's out of 5 choose 2. And we explained that simply by saying, well, there are 5 things and we've got to choose 2 things. But how do we see that on the diagram? It's less easy to see perhaps with this example, the way I've set it out here. So what I'm going to do now is I'm just going to erase these. To see how the denominator works, it's much easier to think about these as just 5 separate things without any labels at all. Or if you like, we can say they're different things: A, B, C, D, and E. How many ways are there then of choosing? Let's use a different colour again. How many ways are there of choosing A, B, C, D, and E? Taken 2 at a time, so there's only 2 things that we're choosing out of a possibility of 5. Well, to understand that, I'm just going to draw this out using my A, B, C, D, E notation. So if I've got to take 2, I might as well start with A, and then I've only got 1 slot left for these 4. So I've got A and B. That'd be one option, one pair I could choose. I could again have A, but this time C, or I could have A and D, and A and E. Now, let's consider if I chose B first. Let's put that here. Now, I can't choose A again because I've already chosen this A-B combination, so that's ruled out. So this time I can't choose B because I've already chosen it. I have to choose C. So BC, and I've now got BD and BE. And now we've got the C. Well, again, I can't do anything but start here. I can't choose CA because I've already got AC. I can't choose CB because I've already got BC. So CD or CE. And finally, if I take my D, I can't choose DA, DB, DC, or DD, so it's got to be DE is the only option that I've got here. And E, obviously, I can't choose any of these because I would be repeating some combination that I have up here. So if we look at how many we've got here now, we've got 4 on this row, we've got 3 on this row, 2 on this row, and 1. So the total number of combinations as predicted by the formula that we are using is 10, which is exactly half the number of permutations that we have around the outside here. So the total number of possible outcomes are permutations. We've got 1, 2, 3, 4 times 5 is 20. So 10, as we might expect, is half of 20. So that gives us our denominator, which is 5 choose 2. 5 choose 2 is 10. So we've got 6 divided by 10, which is 3 divided by 5.